Hello, in this video I will demo or develop and work for scheduling using cultural algorithm. First I will explain a little bit about what is a cultural algorithm. In cultural algorithm actually we have two main components called the belief space and population space. In population space is can be like a genetic algorithm and colony and so on. But in belief space we have more like a knowledge regarding our problem, and using that knowledge the belief space can direct the population space and direct them to the better and better solution. So there are some functionality and interface between them. The belief space can influence the population space. So once we create a new population, belief space can influence and direct the population to go through the better solution. Once we have a new population, and once we have a better result, a better solution, and so on, those best solutions called elites can be accepted to the belief space. So then belief space can use those elites to direct to create a new generation. Okay, so let me talk a little bit more about the presentation of our work. First of all, how we encode our workflow scheduling solution. So supposedly there are I virtual machines and K tasks in the workflow. A workflow scheduling solution is represented by a K element vector. We call it solution, and the K is the K task, such that the solution Tk indicates the virtual machine to which task K is mapped. For example, take a look at this this solution, workflow scheduling solution, 1 2 1 2 3 1. So it means task 1 and task 3 and task 6 are mapped onto the virtual machine VM1. Why VM1? Because the value of these indices is 1. Similarly, task 2 and task 4 are mapped onto the virtual machine VM2, and task 3 is mapped into virtual machine of it should be, let's say, task and task 5, because 1 2 3 4 5, task 5 is mapped in virtual machine VM3. Okay, this is the way of our encoding. For the fitness function, the goal here, actually, before that, the goal here to minimize the workflow execution costs. And once with the concern of the deadline, once we know the deadline, we want to find a solution that minimize the cost and meet the deadline. So workflow maximum should be less than or equal to the D as a deadline. For the fitness function, we use this fitness function. We normalize them. So once we have a D as a deadline, M and max span C as a cost, and max cost is the maximum cost of the solutions in a population. So once we generate a population for each of the solution in the population, we have a max span and cost, and the max cost is that maximum cost of the solutions in that population. Then F score can be calculated in this way. So if for each solution, if the solution max span M is less than or equal to D, it means if they meet the deadline, then we try to give them the number more than 0.5. So F score, the range is between 0 and 1, is normalized between 0 and 1. And for those solutions which they meet the deadline, we give them the score from 0.5 till 1. And if they don't meet the deadline, if in the solution they don't meet the deadline, then their score will be less than half until 0. Okay, so this is a fitness function. So let's go for next step. Let's consider an example. So supposedly this is our workflow. We have about 7 tasks here. T1 start the entry task. We have T2, T3, T4, T5, and T6, which they can run in parallel. And T7 is the exit task. And this is just some information regarding the machines and the data dependency size and task and so on. So by this information in this table, we can have a weighted graph. Okay. Okay, so number of tasks is 7 then for that example. Number of VM, by running the para degree of that example, it can be like a 5. We suppose that the deadline is 500,000 seconds. Para degree once is run, is created, it can give us a 5 because we can run T2, T3, T4, T5, T7, totally 5 tasks in parallel. So the number of VM can be 5. So in first step, we just run and create the randomly generate the population. As you can see here, we just put 5 solutions. Supposedly these are the solutions: solution 1, 2, 3, 4, 5, and each of these number means the VM number, and the index is the task number. And for each of them, we calculate the max span and the cost associated to it, and then the F score. Max span and cost also is we put some example and formulation here. For example, for max span is a summation of the execution time of running each task, as well as the data movement time. And for workflow execution cost is execution cost of executing each task on each for each virtual machine, as well as the data movement cost. So once we have our first population, and then in step 2 we select the elites. For example, here we decide to select the 3 elites. The number of elites can comes from the input for the algorithm based on the elites rate. So here we select the ID solution 5, 4, and 3. So as you can see, 5, 4, and 3. Why? Because based on their F score, they have a higher F score. So 5 is the best one, then is 4, and then is 3. So we put the solution here, and these are their F scores. After that, we add the best elite, the best solution called elite, to the situational knowledge, which we showed as a situational underscore K. So here the best solution is 5, solution 5. So we add that one, the best solution in the save it, store it in the situation. So the belief space contains two items: situational knowledge and normative knowledge. So first, in the beginning, the belief space is empty. Now we go and then come up with the situational and normative knowledge, and then once we add this, we have these two, we can keep them as a belief space. Okay, the situational K is always the best solution, elite, which in this iteration we added solution 5. And for the normative K, we just go for all the tasks. Here we have a table. We have mean and max, lower bound, upper bound, and the size, which is a max minus minimum. So for normative K, we just take a look of these three elites, okay, and then see what is the minimum number of the minimum virtual machine number, and what's the maximum of that machine number. So as you can see, for T1, for these three, the minimum is 1 and the maximum is 4. The same for the T2, the minimum VM number is 1 and the maximum is 5. You put them 1 as minimum and 5, and so on. So the last one, the minimum is 2 VM number for the T7, and the VM number maximum is 4. Once we put that one, we add the associate F score of them for the lower and upper bound. For example, the lower bound 1 here either is coming from this one or from the this solution, so we add this F score there. And for upper bound is from solution 5, this solution, which is the F score of that is this number, and we add it here. So a lower bound and upper bound, actually these are the F scores whenever we select this the min and max from that solution. And here actually for this one we select the 2 from solution here number 5, or the first solution. So this F score can be as a lower bound, and for the maximum is coming from this solution, and this number is F score is adding here as a upper bound. So mean for lower bound, max for upper bound. Then we calculate the size, max minus mean. For example, here is 4 minus 1 is 3, 5 minus 1 is 4, 4 minus 1 is 3, 5 minus 5 is 0, 3 minus 2 is 1, and so on. So this can be the structure of our normative knowledge. So we have a situational knowledge and normative knowledge. Once we have these two knowledge, we add them to our belief space. So now we have a belief space. So this belief space, so this information in the belief space, they can direct the new generation in the new iteration to generate a better and better solution. Okay, so again here the elite, we have the elite here, so just to add the information. So for the step 3, we go and then find the task votes for each of the tasks. So the task votes for the T1, for example, here in the elite is votes of, or the frequent of 4, 1, 1. So it can be the task vote of T1 it will be 1. Why? Because 1 is repeated in elite, 1 is repeated 2, whereas 4 is repeated just once. So 1 is the task force for T1. Similarly, task force for T2, we have 1, 5, and 4, and because they are all the same, one time they are repeated, so we select one of them. In this case, we select the last one, and so on. So, for example, for the task 3, it can be 5, 5, 5, or select 5. For task 5, the votes of 3, 2, and 2 will be 2. Why? Because 2 is repeated twice, rather 3 is repeated 1. So task vote is a vote of, for each task, it's a vote of the machine that they repeated more. The machine repeated more. So once we have that one for each task, we put them together and create call it comprehensively. So the task vote T1 is 1. So here we create another solution. We call it comprehensively. So it's the base on the majority votes of the elite. So we can say is the elite of elite. So we try to generate a best solution of the best solutions. You can say something like that. So task votes of T2 is 4. We added 4 here, and so on. So we create a comprehensive elite in this way. In SF4, we go and update influence the population using the belief space. Now we have a belief space, right? So we have situational knowledge, we have narrative knowledge, and we have also comprehensive elite. So we have the best solutions stored in belief space. Now belief space can direct the population of the influence them to generate a better solution. So in SF4, first of all, to make an influence is coming with, we call it with the step, we call it DX. So DX can be like a step. We can have a step forward, means 1 plus. We can have a step 1 step backward, -1, and no change. We don't go back forward, it's going to be 0. So how we can calculate that one? So we can say if the VM, a new solution, is less than the VM number of solution, is less than of the VM situational knowledge, then the step, we need to go a step forward. So once we create a new solution and we figured out that solution, the VM number is less than the VM's, the elite situational knowledge, as you may remember, it will be the elite. So we will direct the new solution going toward this elite. So we need to have a step forward. Similarly, if the VM solution is greater than the VM elite or situational knowledge, so it means we need to go a step backward to go closer to the elite, to the best solution. And if not, randomly the solution generated a VM number for each task is equal to the best solution situational knowledge. So we don't need to change them going backward or forward. So let's see here how it works. We have the solution. We want to create a new solution, a new generation. This should be DX. So solution situational K, the elites of the previous one is 4, 1, 4, 5, 3, 5, 2. And solution 1 is, for example, 4, 5, 5, 2, 2, 3, 1. The first solution. So once we want to create a new solution now, first we calculate the DAX by the definition here. As I mentioned, 1 is -1 or 0. So we see the best solution for T1 dimension is 4, VM4. The solution 1 also for the T1 is mapped to 4. So it's going to be the same machine. So it can be this this situation. So dx will be 0. For the T2, in solution 1, the VM number machine is 5, but in ELIT, situational knowledge, the machine number is 1. So it means we need go a step backward to direct and going from VM5 to VM1, right? And we need to know that our VM machines are sorted based on their capability. It means the VM1 we can say is the slowest machine, and VM5 it will be the fastest machine, as you can see in these tables here. VM1, VM2, VM3, VM4, and VM5. So if you have any VM numbers, supposedly we sort them based on their capabilities, CPU, capacity, storage, and so on. So we figure it out and compute the dx. And once we have this dx, the new solution will generate like that one. We have solution 1, we added the dx. So as you can see here, the solution first is 4. 4 plus 0 is 4. So we keep the same machine. For the next one is 5. So 5 minus 1 is 4. So we make them VM number to 4 for the task 2 for this new solution, and so on. So, and the last one is 1. 1 plus 1 is going to be 2. So we add the last task T7 to VM number 2, and so on. For all the 5 solutions, we will go the same way. And we know the solution number 5 was the ELIT. So as you can see, the dx is 0, 0, 0. So we don't have any changes for all the tasks. So the new solution, we keep it as the new solution. So once we have the new solution, we are going to apply to like a genetic algorithm or evolutionary operator called crossover and mutation. Let me explain here. For the crossover, we use a uniform crossover. Suppose we have two solution number 3 and 4 here before crossover, and this after crossover, and the changes is highlighted. The way that we will go, and then for each of these like a task from the beginning till the end, T1 to T7, go one by one, and then use the like a random. We call it random if the random number between 0 and 1. So like a flip-flop, yeah. So if it is a 1 and 0, we change them. But if the random number is 0, we don't change them. So this is completely randomly. So supposedly the first one is this is like a coin, yeah. We use the coin, so no change, so we keep them the same. That for the second task, no change. For the third one is coming 1, for example, not 0. Then we change 3 with 1. So we change it 3 and 1 here. So supposedly with the next one, task 4 and 5, no change. And then for this one, once we use the coin, supposedly it's coming 0. No, it's coming 1. So once it's coming 1, a random number, then it means we need to replace these to a VM number. So this is the way of we do they call it uniform crossover. So for each of the tasks, we start from beginning till end for these two solutions. First we select two solutions randomly, then based on that solution we just go task by task from beginning till end, and randomly we decide if we want to change, replace them or not. Then we operate the mutation. For mutation also it can be also randomly. We decide, so randomly we decide, for example, to change a 3 VM number, and then we will go for that solution. So, and then based on that solution we select randomly 3 of them. For example, here randomly is coming the T1, and T2 and let's T7, and then we decide randomly what number virtual machine number we can assign to it. For example, for the T1, it can be from 4 to 5, so we assign the virtual machine number 5 to it. For T2, 3, and for the T7, it can be 2. So the mutation also can be run randomly. So this is the whole operation we use. So we create a new solution and in the new population by this way. For this example, once we run our algorithm, in the final solution after 50 iteration is create this mapping, or this we can say workflow scheduling solution, and this is like a FS score and 0.77599 and 73. So as you can see, is close to, can be closer to 1. Okay, so this is one example and presentation and the logic of how it works. So here I added I added a table for the symbols, so help you to understand the notations. Here we just show the data structure of the situational knowledge. As you know, the situational knowledge, we call it situational knowledge. Okay, is like just the elite of each population. So is elite and solutions of X, for example, X1, X2, Xn, which is these are, for our example, is a virtual machine number, and Fx here is a FS score. And these are just the data structure of the numerative knowledge. If you remember, we had for each task we have a minimum and maximum. Minimum virtual machine number and maximum. These are selected from the elites. And then for each of them, we keep the fitness score, FS score of the minimum or the maximum of it. These are just a flowchart, so how it works, and these are here also is like a pseudocode for the main algorithm. So the way I explain in presentation is coming here just a pseudocode. So as you can see, create a population, then you give them create a max span, calculate the cost for an FS score. Then it goes and then select the best one, at least added in the knowledge space, and then knowledge and situational knowledge. Then updated the belief space based on that. Also, let's go and then create the numerative knowledge of the belief space. So once we have the belief space, now is the time to go and then generate a new solution under the direction of the belief space. Okay, and then here also to our helper algorithm 1 using the product degree, which is identifying the maximum number of the VM that we need to use or we can use. So it can be show actually the maximum number of tasks in a workflow that we can run in parallel. For example, for our example is 5, because we can run T2, T3, T4, T5, and T7 in parallel. And also, this is just a function for updating the belief space. So whenever we have a new generation, based on the like alias and so on, we can calculate the situational knowledge and numerative knowledge. And once we have a situational knowledge and numerative knowledge, we can build our belief space. Okay, this is just an explanation about and presentation about our workflow scheduling using cultural algorithm. Also, the algorithm is developed in R for that example, and I can run one example here for this cultural algorithm with the five machines, 7 tasks, and this is the 5100 is the deadline. You can also specify here some of their argument and factor like a crossover rate, mutation rate, number of iteration, and so on. If you don't assign them here, by default, the program is already assigned. So once I run this one, and let's see, okay, I need to load it again. Okay, let me load it again. Yeah. It's loaded, and then on the following. Oh, okay, sorry, this should be first. It should be this way. Yeah, so it should be first. The first argument should be first the number of tasks, then number of machine, and then deadline. So that's the reason I got the error here, because I did the wrong argument. So number of tasks is 7, number of machine is 5, and the deadline is 500,000. So you can go through the iteration, and as you can see, so the FS score is go higher and higher and closer and closer to 1. So, and then the final solution found in this solution 3332334, and with the FS score of 0.74, and these are the costs and max span associated to this solution. And here you can see some plots regarding to that one. Okay, thank you for watching, and please let me know if you have any comments and feedbacks regarding this presentation or our algorithm. Thank you for watching this demo.